We're going to look at the Winkler method for determining biological oxygen demand, and we're going to look at some sample questions. We're going to look at three different levels of question. The very first one is really easy in that it will give us titration results for the first titration in the Winkler method and the titration after 5 days. So all we have to focus in on in order to work out the biological oxygen demand is step 4 here, which is subtracting the second value from the first value. Then we'll go on to a more difficult calculation where we will look at how to actually take your titration results here and use those to calculate the concentration of oxygen in milligrams per litre. And then the final calculation, we will have two titration results, and we'll have to work through the whole process from start to finish, getting the dissolved oxygen in the first sample using your V1M1N1, getting the dissolved oxygen in the second sample, doing your subtraction to find out how much oxygen was used up in the 5 days, and even taking into account a dilution factor. So let's look at the first example, which is taken from a Leaving Cert paper. To find the biological oxygen demand of a sample of polluted river water, 25 centimetres cubed of the water were diluted to 1 litre with well oxygenated pure water. 2 bottles A and B were filled with the diluted water and their dissolved oxygen concentrations were determined. The analysis was carried out immediately for bottle A and 5 days later for bottle B. The results obtained were 12.8 parts per million and 8.2 parts per million respectively. So the first question that we're asked there is, why was it necessary to dilute the polluted river water? So the reason you need to dilute that river water is that if it's polluted, and that's why I've underlined the word polluted up here, if it's polluted river water, there's a risk that there won't be enough oxygen left in your sample B here after 5 days. It'll already be fairly low in oxygen when you take it on day 1, but then by the time you come to day 5, there won't be enough oxygen left in there for any titration result. So you'll get an inaccurate result in day 5, or maybe no result because there's no oxygen there at all. So to answer that question, you need to say that you have to dilute the water, because if you use the undiluted water, there might not be enough oxygen present after 5 days to get an accurate result by titration. Okay, so number 2, under what conditions should bottle B have been kept for the 5 days? Oh, sorry, I should have answered the second bit there. What was the advantage in using well oxygenated water for this purpose? So the reason you dilute it with well oxygenated water is to ensure that there is enough oxygen there at the start to give you an actual measurable amount of water after 5 days when it finishes. Okay, number 2. Under what conditions should bottle B have been kept for the 5 days before it was analysed? So we know that that's in the dark and at 20 degrees Celsius. In the case of one of those conditions you have stated, explain why it is necessary. So why in the dark? That's so that any little plant material in there can't do photosynthesis, because if it did, that would release oxygen into the water sample, and so your results after 5 days would be inaccurate. It'll be showing more oxygen than it should. And then if you wanted to focus in on the 20 degrees Celsius, that is because the solubility of oxygen in water is affected by temperature and the use of the oxygen, the rate at which the oxygen is actually used up by biological processes in the 5 days is also affected by temperature. And then the next one, what is the BOD of the polluted river water? So this is the maths bit, but it's a very easy one in this case. So in order to get the BOD, biological oxygen demand, you have to subtract the dissolved oxygen on day 5 from the dissolved oxygen on day 1. Dissolved oxygen day 1 minus the dissolved oxygen on day 5. You don't have to write that out like it's a formula or anything. So what did we have? The results obtained were 12.8 parts per million on day 1 and 8.2 parts per million on day 5. So that's 12.8 minus 8.2 parts per million. So my answer for that is 4.6 parts per million of dissolved oxygen. That's my biological oxygen demand. Now I need to just check back in and see if there was any dilution factor. So there was. We had 25 centimeters cubed of the water diluted to 1 litre. So we have a 25 centimeters cubed were diluted to 1 litre, so that's 1000 centimeters cubed. So that is a dilution factor of 40. And what do we always do with our dilution factor? We multiply. So our 4.6 parts per million needs to be also multiplied by 40, and that will give you 184 parts per million as your biological oxygen demand. Okay, so that's your first example. As I said, the first one is easy enough. Let's just move on to an example now of how you would work this out based on titration results. So in a Winkler determination of dissolved oxygen in water, 100 centimeters cubed samples of water were analysed. The iodine liberated in the experiment was titrated against 0.02 molar sodium thiosulfate solution, and the average titration figure was 5.7 centimeters cubed. Calculate the amount of dissolved oxygen in the water in parts per million. Now, before we start working on our V1M1N1 here, I just want to take you through the process of the Winkler titration so that we can see how we work out our reaction ratio between our oxygen and our thiosulfate. So at the very start of this process, when you have just harvested your bottle of water, you perform a reaction that converts your Mn2 pluses here to Mn3 pluses, and that, if you remember, is formed as a white precipitate. But the bit that we're interested in here is for every 1 oxygen you have here, you are getting 4 of your manganese hydroxides, your manganese 3 hydroxides. Now, then the next reaction that we have to look at is what happens to those manganese 3s. When they react with your potassium iodide and your sulfuric acid, you liberate some iodine and some water and manganese 2 pluses. Now, the product that we're interested in here is our iodine, because that's what we're going to determine the concentration of by titration with the thiosulfate after this. So now we know that for every 2 manganese we have, we get 1 iodine. So if we had 4 of these Mn3 pluses formed in the first reaction, we need to double this. So we will produce 2 iodines. And then the final titration reaction that we do is between iodine and thiosulfate. And you'll remember this one, we did it a good while back in our redox chapter, and we produced the following. So your reaction ratio there was every 1 iodine reacted with 2 thiosulfates. So if we have 2 iodines coming through from this guy, we're going to multiply that by 2, which means we multiply this by 2, which gives us a 4. So what is our overall reaction ratio? We start with 1 oxygen and indirectly it is reacting with 4 of our thiosulfates. And we're going to use that to fill in our V1M1N1. So let's just carve out a little space for ourselves over here and do our V1M1N1. In this titration, what was our volume of oxygen was 100 centimeters cubed. 100. Our molarity of the oxygen is what we're trying to work out. And then we've just worked out what the N is. It is 1 for the oxygen. And then if we do the same for our thiosulfate, so that's the reducing agent here, so the volume of the reducing agent in this case was 5.7 centimeters cubed was our average titer. So 5.7. Okay, and our molarity, also mentioned up in the question, it was a 0.02 molar thiosulfate. So the molarity is 0.02 molar, and the N, which we've worked out over here, is 4. Now if we fill in then our V1M1 over N1 is equal to V2M2 over N2, we will have 100 by the molarity that we are trying to work out over 1 is equal to 5.7 by the 0.02 over 4. And when we work out our molarity, we get 0.000285 moles per litre. Now, that is your concentration of your oxygen in moles per litre. We then want to change that into parts per million. Now, we are pretty familiar with this process from the previous examples in this chapter. Let's just carve out another little space for ourselves so that we can keep this all on one page. So we want to go from moles per litre, first of all, to grams per litre. And we do that by multiplying by the RMM, which for oxygen is 32. So we have our 0.000285 multiplied by 32, multiplied by 32, and that gives us 0.000912 grams per litre. So 0.00912 grams per litre. Now we are looking for parts per million, and we know that parts per million are the same as milligrams per litre. So right now I'm in grams per litre. To get it to milligrams per litre, I need to multiply, milligrams per litre, I need to multiply by 1,000. So if I take my 0.00912 and I multiply that by 1,000, I get 9.12 milligrams per litre. So if I have 9.12 milligrams per litre, I have 9.12 parts per million of dissolved oxygen. So that's your second example where you're working out the dissolved oxygen from a set of titration results. Now, just to flick back to our earlier example, so far we've done a calculation where all we had to do was subtract. We were given the 2 dissolved oxygens, and all we had to do was subtract the day 5 dissolved oxygen from the day 1 dissolved oxygen and multiply by a dilution factor. Then in that second example that I've just done here, we were only asked to work out the dissolved oxygen from one sample. So that's where we did our volumetric, there we did our titration, and we worked through our V1M1N1, and we used our 1:4 ratio. And once we got our concentration of oxygen in moles per litre, we then changed that to grams per litre, and then we changed it to milligrams per litre, which was the same as parts per million. So the third example we're going to do is a full calculation where we're going to be given two titration results. We'll work through our V1M1N1s. Then we'll do that for the first sample and for the sample on day 5. Then we'll subtract to get our biological oxygen demand. So the two results in parts per million of dissolved oxygen, we'll subtract those to get our biological oxygen demand. And finally, we'll multiply by a dilution factor. So here is that question. A sample of water was analysed in order to determine its BOD. A 100 centimetres cubed sample of the water was diluted to 2 litres. So just note there straight away that there's going to be a dilution factor at the end of this with well oxygenated water. 100 centimetres cubed of this diluted solution were analysed by the Winkler method, and 7.15 centimetres cubed of 0.025 molar sodium thiosulfate solution were required in the titration. So there are your titration results on day 1. Then a second 100 centimetres cubed sample was stored under the appropriate conditions for 5 days and then analysed for dissolved oxygen. The liberated iodine required 3.2 centimetres cubed of 0.025 molar sodium thiosulfate solution. Calculate the BOD of the water. Okay, so we are going to do two V1M1N1 calculations, then we're going to subtract the results, and then we're going to take account of any dilution factor. Okay, so let's do our day 1 calculation first of all. So day 1, dissolved oxygen. Right, so on day 1, what has it told us? It has told us that the volume was 100 centimetres cubed. So the volume of the water with the oxygen in it is 100 centimetres cubed. And it has, whoops, sorry, there's the 100 centimetres cubed. Blah, blah, blah. Then the molarity is what we're trying to work out. Molarity of the oxygen, just call that M. And then, of course, the N for oxygen is 1, because we're in a 1:4 ratio. So now let's look at our reducing agent. So the volume of the thiosulfate that was added is 7.15 on this particular day, 7.15 centimetres cubed, and the molarity of your reducing agent is 0.025 molar, and then N for this particular one is 4, because we've mentioned already that it's when you trace through all of those equations, you end up with 1 oxygen reacting with every 4 thiosulfates. Now let's fill in our V1M1N1 is equal to V2M2 over N2. V2M2 over N2. So we have 100 multiplied by the molarity of the oxygen, which is what we're looking for, over 1 is equal to 7.15 is the volume here, multiplied by 0.025 over 4. So that means that 100M is multiplied by 4 is equal to 7.15 multiplied by 0.025, or if you want to get M on its own, M on its own is equal to 7.15 multiplied by the 0.025 over the 100 multiplied by the 4. So when you work all of that out, the molarity that you get for your oxygen, the molarity of the oxygen is equal to 0.000447 moles per litre. Now, just like we've done before, we need to go from moles per litre to grams per litre. And then when we're finished with that, we'll need to go from grams per litre to milligrams per litre, and that's the same as your ppm. So to go from moles per litre to grams per litre, we're going to multiply it by the RMM of your oxygen, your O2. So 0.000447. O2 has an RMM of 32, so multiply that by 32 and we get 0.0143 grams per litre. And now we want to go from grams per litre to milligrams per litre. So we're going to take our 0.0143 and we're going to multiply that by 1,000. And that's going to give us the milligrams per litre, which works out at 14.3 milligrams per litre. And milligrams per litre, of course, is the same as parts per million. So the dissolved oxygen on day 1 is 14.3 parts per million. Okay, now we're going to do exactly the same procedure for day 5 then. So at the end of the 5-day waiting period, day 5, our volume of oxygen, in this case a second 100 ml sample was stored for the 5 days, so it's 100 mils, again 100 centimeters cubed. Again, we're looking to find out what the molarity of the oxygen is, and again our N is equal to 1. And on the other side of this, what are we doing for our volume of reducing agent? On day 5 it required 3.2 centimeters cubed, so 3.2 is your volume of, again, 0.025 molar thiosulfate. So the molarity of your reducing agent there is 0.025, and your N we've already mentioned is 4. So when we want to fill that in, we'll have 100 multiplied by m over 1 is equal to 3.2 multiplied by 0.025 over 4. Do all your magic again and you'll get that the molarity of the oxygen in this case is 0.0002 moles per litre. Now we'll follow exactly the same procedure that we had over here. So moles per litre to grams per litre, we'll multiply this by 32 to get it to grams per litre. And when we multiply that by 32, we're going to get 0.0064 grams per litre. And of course we don't want it in grams per litre, we want it in milligrams per litre. So just like down here, we'll multiply that by 1,000. And when we multiply that by 1,000, we'll get 6.4 milligrams per litre, or 6.4 parts per million. Okay, we're nearly there now. We're on to what was step 4 of our method, and that is to get your BOD. And the BOD is your parts per million on day 1 here, which is 14.3. Take away your parts per million on day 5, which is 6.4, which in this case gives us 7.9 parts per million. Now though, we have one final step to do, and that is to account for the dilution factor. So this is the parts per million in the diluted sample. Our dilution factor, we had 100 centimeters cubed. Whoops, just give me a sec there. We had 100 centimeters cubed diluted to 2 litres. So if we have 100 centimeters cubed diluted to 2 litres, that is a 1 in 20 dilution. So 100 cm cubed diluted by a factor of 20 to give me my 2 litres, my 2,000 centimeters cubed. So I take that 7.9 there, and I'm going to multiply that by 20 to give me the BOD in the original sample, which is 158 parts per million in the original sample. And that's the end of those titration calculations.